We're with Quantum Application Lab, and so I'm here at QSoft. You've probably seen me around. Bart, maybe you want to introduce yourself?
Yeah, sure.
Or Tino?
I'm a TNO, it's actually full-time scientist there, but TNO also part of the application lab, so also supporting these projects.
Yeah, so we work together with the industry to figure out or what to work on quantum applications, mostly for what we can do in the near term, and to also get a better understanding of what problems are relevant in different sectors, and how can we kind of bring the knowledge out there into the world. And so QSoft, we're part of QSoft, and so it's also still kind of figuring out, okay, how can we align the best our work with QSoft? Like, how do we involve the people here? What kind of format is nice for people who's interested? Because people are always open or like free to work with us on projects if you're interested, and it can be a nice way to kind of, well, get an idea of what industry work is like, and what people are looking into nowadays on the more applied side. So with that, let's go ahead. So we are now in the middle of a project with a distribution systems operator, Alliander. So they manage energy grids in the Netherlands. We did already a project with them, and so they are so we've been working on another application. So just a kind of perspective. So there's a lot to say, obviously, about near-term applications, different perspectives. For us, very important to hear all sides of it, because, well, we want to know what we can and can't do, and what can and can't we promise to the people we work with, right? We have to be very careful with that. So curious to hear perspectives. I'm thinking maybe we can discuss it after the talk. And then, the work is in progress. We're in the middle of the project. So also feedback, welcome. If you would do it differently, happy to hear that. So with that, let's go ahead. So the title was Sparse Matrix Reordering. So like I said, the Alliander is a DSO. They manage energy grids, which means that they operate the energy grid for large parts of the Netherlands. And in their kind of daily operations, they have to do many analysis on this grid. And that often comes down to solving large linear systems. And these grids are obviously nicely represented by graphs. So it's a nice kind of topic to work on. And in this community, what is very common, so you can solve these linear systems directly, of course, which you've seen kind of in the top right corner. But because what often happens, you have one grid, and then you do multiple analysis on the same grid, but with different numerical entries. But these entries will be at the same place in your matrix of coefficients. So there's a bunch of tricks developed in the DSO community to kind of do some pre-processing on this topology of your coefficient matrix to then make all the future all the future computations faster. So that's kind of what goes on in the bottom left. Once you do this kind of, that's where the main bottleneck is. You do this pre-processing on the left box, sparse matrix reordering, and then in the future you have found this order. You can then apply this order in all the future computations. So we are looking kind of at this process as a whole, thinking, okay, where can we best develop a quantum application? Because obviously there's been some ideas for quantum computers to also solve linear systems directly. So maybe there's something there, but we had to look at the data and didn't really have good condition numbers. So we decided to focus on this sparse matrix ordering, which is also their main bottleneck. And they're also just curious to find out whether this could be interesting. So a bit more about that. I gave kind of high level description. So when you solve this linear system, you can do it doing Gaussian elimination or LU decomposition. It's quite similar. And important to know these grids and so also these matrices are sparse. Important to keep in mind. So, but what happens during LU decomposition is that your matrix factors, you can no longer guarantee that they are sparse because there's this process of fill-in. So you see them, So here, this is Gaussian elimination for symmetric matrices. Or LU decomposition, and here is where fill-in occurs, which means that in your L and U factors, you will have a non-zero entry, where in your original matrix, there was a zero entry. So that is obviously bad, because that just means your matrix will be bigger and your computation time will be worse, and also you're going to need more storage. And so here I mentioned this instance symmetric matrices. So these grids, they are not fully undirected, but they have, every edge goes two directions, but they may have a different numerical entity or a numerical value in both directions. But they'll be incident symmetric in the sense that there will be entries in the exact same places in the coefficient matrix symmetrically along the diagonal. So the actual numerical value may be different, but there will be non-zero entries at the same places. So that in this literature is called incident symmetric. Or they have the same matrix topology. So fill-in is bad, obviously.
Sorry, can you remind what was the factorization? Is it like upper triangular?
Yeah, lower and upper triangular factorization, exactly. So, and kind of the underlying structure of that is Gaussian elimination. So fill-in is bad, we want to avoid it, but it only depends on this matrix topology, so on where the non-zero entries are. So that's kind of why you can do this pre-processing step, because you do all this analysis on the same grid with different numerical values, but with entries at the same places. So if you can reduce this fill-in somehow, it doesn't matter what kind of computation you do. If it's on the same grid, you can use the same order. So this LU decomposition, Gaussian elimination, you can. What happens? The way you iterate, starting here, you can choose in what order you do that by, well, by permuting your matrix. So when do we get fill-in? So let's say because our matrices are incident symmetric, we can eliminate the LU decomposition on columns and rows at the same time, which is called an axis. And then you get fill-in exactly, let's say you start eliminating the first axis, which is entries 4 and 6. Then you get fill-in in 4 and 6. But then, because you've eliminated the first axis, no more fill-in can be generated in that axis. But what can happen is that this fill-in that you've generated kind of trickles down. So that can also generate new fill-in. So you already get kind of the idea. You want to probably start eliminating the axis with the least amount of entries because of this trickle-down effect. If you start eliminating one with a lot of entries, then all these entries will generate additional fill-in. So that's kind of what you can optimize over. And finding, so it only happens after the eliminated axis, and fill-in can cause additional fill-in. So here you see kind of a process of, and you do this until you've eliminated every axis. Which is usually, sorry, yeah, go ahead.
Do they have a bound on how many new entries can come with every process?
I guess it depends a bit on how many entries you have in your matrix. I don't know if I don't have any figures on that myself.
Very few entries instead of full matrix.
Yeah.
Oh.
I think you can go from like sparse to complete, basically.
Yeah, so if you do it in the wrong order, you essentially lose sparse.
Yeah, exactly. So that's the problem.
It's a serious problem.
Yeah, it's a serious problem, but you can also not guarantee that if you do it in a good order, you're gonna keep sparsity. So there's actually some matrices are just bad and they're always gonna have a lot of fill-in. But you can optimize over this. So you can try to find the elimination order which produces the least amount of fill-in. And that's an NP-hard problem, which obviously is challenging because also with a quantum computer, we don't expect to find.
How do you measure fill-in? Maybe you're going to show us later.
Measure, so that would be, for example, here it would be all the entries that were used to be 0 and A and that are now non-zero.
Okay.
So you compare it with your original matrix, then you have your lower and upper triangular.
That's your cost function.
Yeah, exactly. So that's what you optimize over. It is an NP-hard problem. So yeah, we also don't expect to solve this exactly with a quantum computer, but there's heuristics, and maybe we can even a speed up over deterministic classical even if it's a Grover type would still be beneficial. And this is kind of what a lot of near-term applications are focused on, is on this kind of combinatorial NP-hard problems.
Is it also hard to approximate?
Yes. Yeah.
Okay.
And determining the minimal fill-in, this is actually finding.
Yeah, both determining the number of minimum fill-in and also the location is NP-hard. Yeah.
It's even also determining the number is hard to approximate.
Yeah.
To within.
I don't know the exact. Okay, and so this is not super clear way to represent it. So a nicer way is through this concept of elimination graphs. So technical definition, but basically this is, so we have this coefficient matrix A and we let it say it represents we can say it characterizes some adjacency matrix with this graph. So that's the graph we start out with. And then you eliminate an axis during Gaussian elimination. then how you represent this in this representation. Remember this first axis, it had entries in 4 and 6, and it generated fill-in at 4, 6. And so what we do here, we eliminate the first node, and then we draw an edge between those nodes where we got fill-in. And so formally, what you do, you remove a node. That's kind of the step you take in your elimination order. And then you have to make all the neighboring nodes a clique in your next graph. And then you keep doing that. So eliminating nodes by some type of algorithm until you've eliminated all nodes in your graph. And then every edge that you've added at some point during this process is a fill-in. So you can collect all these, so you store all these edges somewhere else. And that will tell you the fill-in you've generated and also where you've generated the fill-in. So this sequence in which the order in which you eliminate these nodes defines your permutation, because it also gives you the order in which you do Gaussian elimination. So it lets you know how you should permute the graph. So you can rephrase the problem as which elimination order of these graphs adds the least amount of edges, equivalent problem. There's classical heuristics to solve this, which I kind of hinted at before. It's called the minimum degree ordering. So you just start by eliminating the nodes with the least degree. And that's
state of the art.
Sorry?
Is that what they actually?
Yeah, that's what's
Okay.
what's most commonly used. And it actually works, I think, perfectly if you don't have any tie breaks. Then you know that this is the best strategy, but that's at tie breaks. So if there's multiple nodes with the same degree, that's when you need to do make heuristic decisions.
Which will often happen for sparse pages, of course.
Yeah.
So,
Yeah. So it's the same problem. So it's still combinatorial optimization problem. And so, like I said, this is kind of the problems that people look at for lots of near-term applications. So by doing QAOA formulations, but Bart will say a bit more about that.
But if you have if your graph is a really nice sort of monotonically decreasing degree sequence and not too much degeneracies, then this works really well in practice, I guess.
Yeah, I mean, it does generally work well in practice. So like with this heuristic, for their numerical data that they have, for their actual grids, it works okay.
Yeah.
But it's hard to compare it to what is the most efficient solution because they can't find it.
Are there any approximation guarantees?
No, so or you mean for the heuristic?
What do you think? Are you within a factor of something?
Yeah, this I'm not sure. We didn't see anything in the literature for that. So
most people work on this are more on the practical side, so they don't actually, they just care about how it works in application. Okay. So yeah, for this near-term applications, we basically considered how can quantum help. So I think I'll quickly go over the basis of adiabatic quantum computing and some implementation of it. I think it's not too new for most people here, but just to be on the same level. So adiabatic quantum computing is just finding the ground states of problem-specific Hamiltonians. You start with an initial easy Hamiltonian, and if you do an adiabatic evolution, I won't say what that specifically means, then towards that problem-specific Hamiltonian, you guarantee to stay in this ground state. If you make sure that this ground state corresponds to the solution of your problem, then you're happy, because then you found the solution. So adiabatically, it's basically, it must be slow enough, there must be not too much impact by noise. Yeah, and then you guarantee it. And this adiabatic quantum computing model is actually a universal quantum computing model. So there's 3 hardware types we've considered, which don't do this specifically, but they at least somewhat approximate it or have ideas of adiabatic quantum computing. First one is quantum annealing. And here you also evolve Hamiltonians, but you don't do it adiabatically. So there's actually no guarantees on staying in a ground state. But instead you do it faster, but you also do more runs. And it turns out that this still gives quite good results. And there's also some guarantees you can even give. But it's not an actual, there's no guarantees, it's actually heuristic. And that's also what it's known for. And the current state of the art for quantum annealing is given by this company called D-Wave. And they are specifically restricted to combinatorial optimization and specifically QAOA or icing models, which I'll explain later if you're not familiar with. And secondly, of course, we have gate-based devices, which can somewhat do adiabatic quantum computing. An example being QAOA. It's not actually doing adiabatic quantum computing, it's more like an approach, an approximation of it. So basically what it does is we want to implement these unitary this evolution through unitary operators, some parameters we need to optimize, and we do this through a classical optimization, through a classical loop, and then a quantum circuit, and then keep running until you minimize this classical function.
Yeah, and so then the third platform is with neutral atom computers. So this is a type of analog computing. It works somewhat similar with to quantum annealing in the sense that you encode your problem solution in some final ground state. So neutral atom computers allow you to place atoms in a grid. So actually here you see them in a 3D grid, and the nice thing is that you can choose yourself how to where to place them. We're working with a 2D grid, and the principle that these computers work on is with something called the Rydberg state. This allows your atoms to be entangled with each other, because if they're too close to each other atoms, then they cannot both be in this Rydberg state. So then, but you can let it be energetically favored for these atoms to be in a Rydberg state. And the difficulty with analog computing is often how do you actually encode your problem in an analog computer? Because yeah, you can have some quantum process, but actually how do you get the information that you want out of that? But this kind of configuration of the hardware allows for a really nice implementation of this graph problem, which is called the max independent set problem. You probably know it. It's finding the largest set of non-adjacent vertices. You see it at the top left. It's an NP-hard problem. And actually, when you implement this on the analog computer, it becomes a bit restricted, the unit disk maximum independent set problem. And so you're placing a requirement on your input graphs that whenever two nodes are within some unit distance from each other, then they have to have an edge between them, and otherwise they don't. And to bring this back to the analog computer, so any two atoms that are within this Rydberg blockade distance from each other are essentially in this unit distance from each other. So if you, like I said in the previous slide, let the Rydberg state be the energetically favorable state, then the final ground state of your system will encode exactly the maximum independent set, because it will try to put the most atoms in this Rydberg state, but it's restricted by not allowing more atoms, like neighboring atoms, to be both in this state. So you have a very natural implementation of this max independent set, or unit disk max independent set. So then the problem becomes, how do you encode the, yes?
I guess the problem does not remain NP hard if you restrict yourself to like this unit disk.
I think it's still NP hard.
Well, don't your graphs become planar immediately?
Sorry?
Don't your graphs become
Yes. But I think there was some, yeah.
I'm sure they become planar.
Yeah, I'm not sure actually. So this is something we're recently started working on together with people from Pascal. So I'm not super deep into the material yet, but this is kind of
can also be closer. Yeah, never mind. Yeah, you don't necessarily planar.
Yeah, I thought it was still a hard problem. So yeah.
But with this Rydberg atoms, you can place them in locations where you want them to be.
Yeah, so that's how you encode. Okay, so that's how you encode your problem instance.
So this does give you a large class of graphs.
Yeah, exactly. Yeah, exactly. So this is how you do your encoding, and so then the problem becomes, how do you actually encode the problem that you are working on in this unit disk max independent set problem? So you want to have some efficient reduction from whatever problem you're working on. And that's kind of why we mentioned these three platforms, because each of these platforms allows you to work with this QAOA formulation so there's also a translation from the QAOA to this unit disk MIS. So you can implement it on the three different platforms. Ideally, you don't have to first reduce it to this QAOA, so quadratic unconstrained binary optimization problem, which Wart will say a bit more about in a minute. And you can translate directly. So the problem that we work on with these elimination graphs, ideally we translate directly to this unit disk problem, but that can be pretty hard. So you don't know actually if this already exists in literature, or so that's something we're figuring out if it's possible.
These are distance graphs, which I think there's good LP approximation algorithms, dependence numbers.
Yeah.
So I think that you can start with an SDP by the lowest data number, and then I think that diagonalizes because of this metric that determines the edge conditions.
Okay.
I'm wondering what the actual numbers are that you could. People study these distance graphs, but usually the infinite settings. So that you consider.
Yeah, here you're limited to.
But this is a subset graph, so LPs still work.
Okay, yeah, would be super interesting to look into that. Okay. So yeah, we have these 3 different hardwares, and that's kind of the point of the project where we are in as well. So we have done kind of most of our classical analysis and formulation. Now we want to try to run some experiments. Yeah, and Mark can say a bit more about this QAOA.
Yeah, it's just maybe by show of hands, who knows what a QAOA formulation is? Okay, not everyone, then I'll quickly explain it. So the idea of a QAOA formulation is, it's in the abbreviation, quadratic interstate binary optimization. So we're optimizing some sort of problem objective function and all the in binary variables, so these xi variables, and all the expression, the objective function must be quadratic in these binary variables. So you have some linear terms and you have some quadratic terms. The basis, that's what it is, and we're optimizing over these variables. So as Koen said, so we had that quantum annealing naturally solves these problems under the devices, for example, through D-Wave. QAOA has a natural implementation to QAOA, and the QAOA is actually equivalent to the maximum independent set problem. So also on this analog computers, you can solve QAOA. So that's nice. So the idea would now be to have this problem that we have sparse matrix reordering, write as a QAOA, and then we can actually implement on these 3 hardware types. And to do that, we basically go back to these elimination graphs, and we need some binary variables. So what are we actually optimizing over? And it is in each round, or in each, we need to find an order. So in each round, we need to choose 1 vertex. So we introduce binary variables for the nodes. So these x and k, is this legible, by the way? It was more legible, I'm not sure. X and k meaning if node n is actually present in this kth graph, or if it isn't. You just keep track of which nodes you have when. And then we have some constraints, of course, in this elimination. Firstly, we can't have more nodes than in the new graph than the graph before, so nodes can't be added. This is first constraint. And secondly, each round we need to remove exactly 1 node. So the behavior of nodes is exactly represented by these variables and these 2 constraints on these variables. And of course, we're also interested in seeing what the edges do. So we have a similar binary variables for that. So if a certain edge nm is in the kth graph, it's this y nmk is equal to 1, otherwise equal to 0. And then the only constraint that really is on the edges is this maybe hard expression, but I'll shortly go over it. So basically the edge in the next graph will be, there will be an edge, the nm will be in the next elimination graph, either if it already was in the elimination graph, that's this. So if this k+1 graph, whether this edge is in there, then either it was already in the previous graph and the 2 nodes are still in this next graph, so they're not eliminated, or it gets added by this fill-in. That means that this node v, so that's the node we remove in this next elimination graph, this was connected to both n and to m. So this node that we remove v was a neighbor of both n and m in the previous graph. Now we remove it, so we need to add this fill. So this is a constraint, and you already see this is somewhat quite a high degree constraint, it seems, because if you want to move this into like a quadratic or at least polynomial expression, you indeed get a degree 5 on the top of my head. Okay, so now we have this, we have these binary variables, we have these constraints, and there's standard methods in QAOA formulations to move these constraints, because the QAOA was unconstrained, you can't have constraints, but you can move them into the objective function through standard techniques by so-called penalty functions. And then we need to minimize the number of edges that we add. And in each round, you can just check, well, the number of non-edges, you can just check, was it in a new graph, well, it wasn't in the graph before, all the different rounds. So in the end, the objective function will be this, plus a lot of penalty functions. Because you can see this is quite an involved expression. So there will be a lot of extra terms. And this is quadratic, so that's nice for the QAOA. But it turns out if you actually want to also add the penalty function, it results in a 6th order binary expression. That's mainly from this hard constraint from the edges. And luckily, there's also standard techniques to actually reduce this degree back to quadratic. Unfortunately, that's quite some extra overhead required for that, quite some extra binary variables. In particular, you can compute it as a quartic number of auxiliary variables. As I said, there is some optimization we can do. So now it seems a bit of an overkill that we kept track of edges everywhere, for example. Instead, we can consider when an edge is being turned on, and there will at least be less variables which has to equal 1, which turns out to be better. Fortunately, still we have this quoting number of variables. The constant becomes smaller, but it's still actually too large. And I said we're looking at this near-term application, so we really want to implement it on hardware already. And if we have a quoting number of variables, well, then it very quickly becomes infeasible. So to actually make it possible to still actually show early on that, well, we can do this on the near term at least, we've considered something else. I think Koen will explain that.
Yeah, so we decided this is not so nice for implementation, so we kind of went back to the classical literature to see if we could do better. And we found this concept called the minimum chordal completion. So what ends up happening, the problem itself, the minimum chordal completion problem asks you how many edges do you need to add to a graph to make it chordal complete. And it's chordal complete if no loop larger than 3 has no chord. So is, how do you say that? So a chord is something that cuts through a loop, an edge that cuts through a loop, and you want every loop larger than 3 to be chorded, and then it's chordal complete. And how this relates to this previous representation of elimination graphs is that you have your whole sequence of elimination graphs, and every time you keep adding edges, right? These are fill-in, and you collect these edges in a set. This set is called your triangulation or your chordal completion, because when you add this set of edges to your original graph, you will have a chordal complete graph. And this is called triangulation because you're turning every loop into a triangle, basically. So that's a really nice representation because then you can work with this problem definition instead.
Oh, wait. So you're saying like the problem of minimizing the number of edge addition actually reduces to this?
Yeah, exactly. Yes,
Actually, it's equivalent to.
it's equivalent. So it's also NP-hard problem. The only difference, so essentially the big difference is conceptually is that here when you've solved this problem, you will know where your fill-in will be, but you don't necessarily have found the order which will produce that fill-in for you. So in that sense, it is a bit easier, but it's actually, it ends up being equivalent because you can find that order from knowing where the fill-in occurred. So that's kind of what is described here. So you input your graph, you do some algorithm, can be anything to find the chordal completion of that graph, but now you want to bring it back to an elimination order that generated that chordal completion, and you can do, and there's an efficient method for that. It's called the lexicographic breadth first search, and it finds you the nodes, the order in which you should eliminate the nodes to generate this triangulation or chordal completion. So this is kind of what we decided to work with because we found this idea, which is called, this optimization idea, where essentially, so there's a pseudocode. You start with some with this input graph, which represents this coefficient matrix, and then you start a loop where you first check if this graph is chordal. If it's chordal, then you have a perfect elimination order, so you're done. Then, if it's not, then you actually add constraints to your optimization step. So you find a random loop in this graph. It's not chordal, so there must be some loop that's not chorded. And then you add a constraint that says that this loop needs to be chorded during your optimization. And then you do an optimization step. And then you check again, okay, now is the output chorded? No, then we add another constraint. So we keep adding constraints for every loop that remains in the graph. We add, okay, also close this one, okay, to put a chord in this loop, until we actually get an output that says it's chorded. So to guarantee that this works, you're going to end up with an exponential amount of constraints because it's an NP-hard problem. But numerically, testing this, or at least classically, we saw that you often need only a small number of constraints to end up at a chorded graph. So that's kind of what we want to test now, to actually have a QAOA for this. So what we will do is run this optimization step on a quantum computer, so using one of the 3 platforms that we showed, and then doing the rest of the loop classically. So checking whether your graph is chordal, you can do it efficiently. Finding your elimination order from a chordal graph, you can also do it efficiently. So the main bottleneck is adding chords to this graph. So that's where we are now, and that
You choose these loops randomly? Or?
Yeah. So there's an efficient algorithm that finds you loops, and you take an arbitrary.
I mean, presumably, depending on which loop you choose, you might get different quality of your findings.
Yeah, I imagine. I mean, we haven't.
Maybe extra heuristic for choosing.
There's this heuristic for actually when you have this many constraints called Bender's cuts. I'm not sure if anyone has heard of it. basically it doesn't mean just randomly add the constraints. There's this you basically add constraints in different ways. I'm also not the expert on this, but there's different ways in which you would multiple constraints at the same time, and in some way this is a heuristic which gives quite good results.
But this is for adding the edges. Like I basically I was thinking about choosing this loop.
Yeah, so I'm sorry, I meant adding the constraints. So adding these constraints it happens somewhat randomly in a sense, but then you do it multiple times, because of which heuristically you get decent results.
Yeah, I imagine the loop selection could probably be optimized. We haven't really looked into it. It would also happen classically, so if we find some classical method for that, then we could easily use it as well. Yeah, so that's kind of, oh yeah, and then we do more kind of, because we're limited in what hardware we can use, we try to do as much classical pre-processing and post-processing as possible. So there are things you can do with your input graph already that are easy that you can know. For example, a leaf in your graph will always have to go first in your elimination order. So you can already look for leaves classically, and the same with certain types of loops. You know you should start with those after the leaves. So there are certain things you can do classically that you can already say these need to happen in front of at the beginning of the order. You end up with this reduced graph, which then will still be hard to compute the elimination order over. That's what we do quantumly. And then we need to do the post-processing, right? Because we end up with this chordal completion. We don't end up with an order, so well, we have to bring that back as well. So that's kind of the larger pipeline we imagine, and then this needs to be implemented in the larger grid computation pipeline as well.
How many nodes are we talking about when you guys?
Yeah, so we receive data sets of around 600 nodes, which is kind of the smallest, like what's relevant. And we
city level, small city level.
Yeah, exactly. It's like a small city. And with this pre-processing, we reduced it, I think, to around like 50 nodes, yeah, something like that. That we would try to embed then on the quantum computer.
That's the Sparse. So that's the QAOA.
Yeah.
Is solved on an instance of.
Yeah, exactly. Yeah. That's what we want to do.
So if there's QAOA had a quadratic and a linear term. If there's no linear term, then there's classical approximation algorithms. Problems.
Yes.
Approximation factors roughly logarithmic.
Yeah.
So 60 is not so bad.
Yeah, of course. So
but actually, this logarithm is more refined. It's actually the logarithm, the chromatic number of the graph given by the support of the matrix that defines these interactions. So it's good also to look at the chromatic numbers. If these are very small, you might get very good efficient.
That's a very good point, and it's good to mention that these examples that we get from Aliander, they are like, they don't want us to solve it better than they already can. They're very happy with their classical methods, which I assume they're also researchers. There's probably methods like these they work on, but especially if they want to scale, they see that they need to implement more edge, need to like build new networks, etc. So they need to scale to the million number of nodes. They need methods which work on that level, and there the classical becomes actually.
Yeah. The data we got was mostly because we told them, okay, give us the smaller sets because we cannot embed anything big. But that's for that they don't need quantum computers to solve these problems.
So these graphs, they represent like the network.
Yeah.
Electricity lines.
Yeah, exactly. So a station is a node and a
Yeah,
cable.
but here's an out of the box idea. Like, why don't they build a network in such a way that's easy to
That's a good point.
I'm sorry, we have to put a substation in your house because the network will be easier to diagonalize.
Yeah,
That's
no,
like Aliander.
yeah.
I mean, honestly, that's probably easier than building a quantum computer.
That could be a nice direction when someone is getting involved in city planning or something.
Yeah, exactly.
Well, these networks are going to change dramatically in the near future because we're all generating energy these days.
Yeah,
right?
Yeah, and also using twice as much electricity.
Yeah, so we're working for some context together with like the department of Aliander that's really looking ahead 10 years in the future. Okay, what are the challenges that we as an organization have to deal with at that point, and what technologies could be around then or later that could help us. So that's kind of also what makes this collaboration nice. Like, I don't expect, some kind of solution really soon for this problem. So they expect to have to double their grid size in the next 10 years to what they did over the last 100 years. So there, and then the additional complexity of also offloading energy onto the grid. So they're really looking into alternative methods. So yeah, and then, so this is kind of this pre-processing that I talked about, right? There's easy parts, classically removing leaves, shrinking loops. So here you see, like once you've removed the leaves, then loops that kind of look like this, you know, you can do those second in elimination order. And yeah.
So yeah, and there's also pre-processing steps you can think of classically which are better. For example, if you would remove a node in a clique, that would actually add no fill-in as well.
Yeah.
The only problem is that's also hard.
Yeah, because all its neighbors will already be a clique.
Exactly. It's also hard, but then that's other things you can think of as the graph.
And I think that's it. So yeah, if there's, it was maybe a bit fast, but also because we were happy to have some discussion or some questions. Or so we are quite far in the project, so maybe going all the way back to the beginning is not so nice anymore. But still, it could be nice to take any feedback also into future projects and what ideas we can think about. If we think this is a super interesting project to work with for Alliander, we can also say, maybe we do a second one, and we should really look into this particular area.